Okay, guys, I hope you had a great Christmas break. Now, I know we only have 4 days left before then we kind of break again for finals, but I told you after chapter 18, chapter 19 through 25 is 40% of the AP test. So we really need to make sure we understand and we hit it hard so that we can really excel in this part of the test. And I don't really do that stuff like, oh, my teacher's gone, so I don't have to learn. I'll just use that as an excuse. No, absolutely not. So this video is for if you have already read chapter 19, which you were supposed to have. If you haven't, you need to stop and read it. I think a lot of the times we have not been reading the book and taking the notes, and then when I give you an overview and a summary, that's all the learning you get is the overview. So you don't have the details, you don't have the why and all of that, and that is showing up to hurt us major. Okay, so chapter 19 is confidence intervals for proportion. So in chapter 18, we were doing sampling distributions. Confidence intervals are based off of sampling distributions, but we're just doing proportions. And I found it funny that was one of the hardest questions for some of you on the test for chapter 18 is it a proportion or is it a mean? Is it categorical? Is it quantitative? So if you're having trouble with that, make sure you ask yourself, like, what kind of question is being asked here? If I was doing the sampling, what kind of responses would I get? So this example that we're doing for chapter 19 is about C fans and whether or not they are diseased or not. So if you were the one collecting the sample, you would go to the C fan and you would say, is this C fan diseased or not diseased? So your answer would be yes, no, sick, healthy. So that is categorical because it is a yes or no question. There's only two categories. I'm going to divide the C fans into a diseased category or into a healthy category. So categorical. Just because it has numbers doesn't mean that it's quantitative. This is math. We're all going to have numbers, but it's what do the numbers represent? So for this, these numbers represent the proportion of C fans that are sick. So in our sample of 104, we have 51.9% are sick. And notice this is P hat. It says we took our own sample, and that's what our sample said. So if every one of us went deep sea diving and we all took a sample of 104 C fans, we wouldn't all get 51.9. You might get 50.2. You might get 53.4. You might get 50.8. We don't know. There's natural sampling variability, and that's where the stuff from chapter 18 comes into. If we were to all do that and we were to all plot our P hats onto a graph, they would become normal and they would line up at the population proportion, exactly how many C fans are sick. But we don't know that, and we're not going to do that. Otherwise, we would just take, hey, look, I'm at school on a Monday and the bells are still on. We would just do that and we would have the right thing. But that's never going to happen in real life. So what we're going to try to do now, we know in La Stats Land, if we actually did that and we all took samples and we all lined them up, then they would be a normal model and they would be, all of our P hats would go under here and they would all line up and the center would be P, the actual proportion of C fans who are really sick. We don't have the time nor the money to do that. So what we're going to do in this chapter is we're just going to take our one sample, and knowing that this distribution happens, we're going to talk about, well, what do we know about the population of C fans, the whole population, just based on my sample? What can I say? Okay, but we know our sample is not the gold standard. It is just one of many. So we're not going to say too much. We're going to have to talk about it probably. We're 95% confident. We're not going to be 100% confident. Okay, so we're going to use our P hat, which was 51.9%. And then we're going to make our own model centered around our P hat. Now, we know that this is just our sample. It's not the exact population, but we're going to use our sample to represent the population. So think back what we did in chapter 18. Well, we did our normal model, And then we moved out a standard deviation at a time. And this was our formula for standard deviation, square root of PQ over N. Because they gave us P, the population proportion, and so then we could find Q, and then we know what our sample size was. Well, from here, that's not realistic. In real life, we don't know what P is or what our standard deviation is. If we did, we wouldn't be needing to do this. The whole point is that we take samples because we don't know about our population. So instead of standard deviation, we're going to do standard error. We had like a 4-second chat about this in chapter 18. It is not real life that we would actually know P, so we couldn't ever actually find the standard deviation. So we have to use the next closest thing, which is called standard error. It's the exact same formula, but instead of using the actual population P and Q, we have to use our sample P and Q, because in real life, that's all we have. We drew a sample. What do we know? Well, I know P is 51.9. I'm hoping to use that to talk about the population, but I don't have any information about the population. So I just use what I have, and I call it standard error instead of standard deviation. Okay, so here's the formula. So our sample was 0.519, which would make Q 0.481, because remember, those have to add up to 1. And then we took samples of size 104, so over N. Notice all of this is under the square root. So I noticed a couple of you on like finding your z-scores and finding this formula, you weren't tapping it into the calculator right. So just put you some parentheses around here anytime you've got multiple stuff on the top. It doesn't matter here, but it does on the z-score, so just get in the habit of that. So just type in your calculator square root 0.519 times 0.481 divided by 104, and then you'll get 0.049 or 4.9%. So we're going to do the exact same thing. Our sampling distribution that we worked on in chapter 18 says, hey, well, this is going to be a normal model. All we have is P, so we're going to center it at P, so that is 0.519, and then we're going to stretch out by our standard deviations. 1, 2, 3 standard deviations, and we're going to go backwards. 1, 2, 3 standard deviations backwards. So we're still going to be able to use our 68, 95, 99.7 rule. So 68 doesn't help me very much. That's not very specific. So most of the time we'll stay with the 95. So what am I able to say? Well, I'm just going to say about 95% of all the samples that I could ever draw should be within 2 standard deviations of the real population right here. Okay, so if I use that and I say that backwards, my sample, P hat, should be 95% of the time, it should be within 2 standard deviations of the real population. So let me come over here and kind of write that over here. So this says the real population P is supposed to be plus or minus 2 standard deviations, or standard errors, because that's all we have, away from any sample that I draw, because the sampling distribution tells us we have to be a normal model. So 95% of the time, this should happen. The real population should be plus or minus 2 standard deviations away from my sample. So I don't know P though, so what I can say is I can flip that around backwards, just simple algebra. I can say that my sample plus or minus 2 standard errors should capture P. All I did was move this to the other side. So I can talk about, well, what should happen with the population? Well, it should be plus or minus 2 standard errors away from my sample 95% of the time. And that is all the whole point of a confidence interval. It's all based on the sampling distributions that we did in chapter 18. It's all based on the normal model that we've been doing. So I'm not sure where P is, but I am sure that 95% of the time it will be within 2 standard errors away from the sample that I collected. And that is as good as I can get. Okay, so what can I say about this confidence interval that I've just found, this range of values that I've just found? So remember when we did chapter 8 and 9 with the linear regression, you had that form sentence for R squared. Well, you're going to have a form sentence that you want to say about confidence intervals too. So you're going to get used to that. You're going to memorize that. You're going to write it 100 times if you're the one actually really doing your homework. But what will happen a lot of times, especially on the multiple choice, is they'll give you a scenario and they'll give you a sentence about the confidence interval and they'll say, what's wrong with this sentence? So that's what we're going to do here. We're going to go through all the things you'd like to be able to say and why you really can't say them. And hopefully you'll be able to pick that out if you have a multiple choice. And hopefully that also means you'll never be the one writing these bad sentences. You'll know exactly what you're allowed to say and what you're not allowed to say. So these are in order of strongest to weakest of what we would really like to say and why we're really not allowed to say that. So number 1 says 51.9% of all sea fans on the Los Redes Reef are infected. Well, if we're saying what we're saying here is we're saying that P, the population, is for sure equal to 51.9, and I don't know that. What I know is that my sample was 51.9, and I'm going to use my sample to estimate the population, but it's not going to be exactly. I'm hoping it's going to be within a range, but I will never know that it's exactly 51.9. Odds are it's not. My sample's probably not perfect. Okay, so a little weaker. It's probably true that 51.9 of all sea fans are infected. No, it's probably not true that they're infected. Now, what they did is they instilled a little bit of doubt right here, which is good. We need some doubt because we're not 100% sure. But what they just said is probably P is equal to 51.9. Well, probably it's not. But I'm going to use a range to tell me. So they're still not getting into that range here. So let's go down to number 3. We don't know exactly what the proportion of sea fans on the Los Redes Reef are infected, but we know that it's within the interval 51.9 plus or minus 2 standard deviations. So we know that it's within 42.1 to 67.1. So we're getting there. Now we're within the range. Now we're telling people we don't exactly know what P is, but we know it's around here. The problem with this is right here. I wish I knew that, but I don't in fact know that. Because remember, I only did 2 standard deviations. So that means I'm only 95% sure on my normal model. So I can't say that I know it. Okay, last one. We don't know exactly what the proportion of sea fans are, but the interval from 42.1 to 67.1 probably contains the interval. Now, this statement is true. It just doesn't sound very like you just did a bunch of math to figure this out. It just kind of sounds too wishy-washy. Everything in it's true, we just want to shore it up a little bit. So here's your form sentence that you want to start to memorize right here. We are 95% confident that between 42.1 and 61.7% of the Los Redes sea fans are infected. So let's look at what all this entails for a perfect sentence. 95% confident. So we're telling them our confidence level, we're giving them the range, and then we're putting it in context of the problems. The Los Redes sea fans are infected. Now, I only took my sample from this population, the Los Redes sea fans, so I have to include that. If you just said, I'm 95% confident that between blah, blah, blah of sea fans are infected, you would be making a statement about all the sea fans in all the world, and you're just not doing that. You only sampled Los Redes sea fans, so you need to only make a statement about that. But this is where it's at. You want to write sentences just like that. Okay. One of the things you have to do, we're going to add more and more and more to this as we go throughout the semester. We're going to learn different kinds of intervals, and one's about proportions, one's about means. So what you have to do is you have to name these on the AP test, and they're named exactly based on what they are. So this shouldn't be complicated. It's just a step you have to remember. This is a 1 proportion Z interval. We took 1 sample of fans, so 1. It's a proportion because it's categorical. We did the proportion of sick fans. You're sick or you're not. We used the normal model, so we based it off of Z-scores, and we'll get more specific about that in a minute. And then we did a confidence interval. So all of these words mean something, and they're all important. 1 proportion Z interval is what we just calculated. All right, all of this 1992 presidential election, the Gallup, they surveyed people. At that time, 62% said that they might switch their votes later. We came back, so here's what we really need. In June, we surveyed 909 registered voters and asked them, are you likely to switch your vote? 18% indicated that there was a chance that they might switch. So they calculated a 95% confidence interval. So 18 is p hat. And then they did plus or minus 2 standard deviations, or 2 standard errors rather, away. And they got the range 15.5 to 20.5. So let's go through these statements that they're about to give us and see if we can see which one's right and which one's wrong. Okay, why don't you pause and try to read through these and see if you can see what's right about these and what's wrong about these, and then I'll go through them with you. That way you can actually kind of have a test by yourself. Okay, so pause and do that. All right, number 1, in a sample of 909 registered voters, somewhere between 15.5 and 20.5 of them said there might be a chance to switch their vote. Well, in the sample, I know how many people said they would switch their vote. In the sample, 18% of them said they switched their vote. What I'm trying to discuss here is, based on the sample, I think somewhere between 15.5 and 20.5% of the population would switch their vote. So this is not, you're actually being wishy-washy on something that you're sure of. I'm sure in the sample, 18% said they'd switch their vote. So that one's out. Number 2, we are 95% confident that 18% of all registered voters have some chance of switching their vote. Well, that is p hat. We're 95% confident that p hat is true, and we're not. We need the range. They never put in the range here, so I can't just talk about my p hat. I have to talk about it in a range. 3, we're 95% confident that between 15.5% and 20.5% of all registered voters have some chance of switching their votes. This is the right one that you want right there. It has the 95% confident, it has the range, and we're talking about the population instead of our sample. So ding, ding, ding. In context. 4, we know that between 15.5% and 20.5% of all registered voters have some chance. We don't. We're only 95% confident, so don't overstate yourself. And number 5, 95% of all registered voters have some chance of switching their votes. No, this is mixing it up. We're 95% confident, and then we give the range of who has a chance to switch their votes. Okay, I'm going to stop this video here since we're almost about halfway through. I just don't want to make the videos too large. So we'll just pick back up right here on video number 2.